All right, we're going to do a video on dependent t-test, dependent test of the means. And this is basically a table below lists GPAs of college students before they entered a learning community and 1 year after they entered a learning community. Assume the population of changes is normally distributed. We have a very small sample here of only 7. And test the claim at the 10% significance level that the learning community increases academic success. So that we have before, which is the pre, and post. We have 10% as alpha, which is our significance level. And if you were doing this in a TI-84, you could enter the post-learning community as list 1, the pre-learning community as list 2. In list 3, you would make that equal to list 1 minus list 2. And that's all of the differences, or D. This is dependent because we want to test the differences in each student. We don't want to compare, Joey with Susie, because that doesn't make sense to compare their GPAs if they've changed. We want to compare each student to him or herself to see the change in GPAs. So our null hypothesis is that there is no difference. In other words, there's no difference. This learning community did not make any difference in academic success, or they did not raise the GPAs, and the alternative is that the GPAs were raised. This is a t-test. This is assume we have normality, and we can go ahead and write our draw our normal curve, or practically normal curve, our student's t-curve, and this is if assuming we selected all random samples of size 7 from this learning community and looked at the differences in their GPAs, this is what the differences would be distributed with. The null is that there is no difference, so we're assuming the null is true, that there is no difference. And then we look for the standard deviation. The standard deviation is the standard deviation of the differences over the square root of n. We need to go ahead, and if we want to find the actual difference, the actual mean difference, it's 0.23, we'd add up all the differences and divide by 7. That's how many there are. So there was an average of 0.23 difference, an increase. That is an increase in GPA, but we're saying, is that increase due to chance, or is it actually due to this learning community working? So we want to find the standard error, which is the standard deviation. I've input this list 3 into my calculator. I found the mean difference and the standard deviation of the differences. The standard deviation of the differences is 0.22. I divide that by the square root of 7 to get the standard error, and the standard error is 0.03. So about 68%, this is not completely normal, but a good proportion of the differences that we would get would be plus or minus 0.08 in their GPA if this was just due to chance. We got 0.23, that's obviously out in the tail. It looks pretty out in the tail. We want to find the test statistic to see how far out in the tail that is, how many standard deviations away from the mean that is. The mean difference is 0.23 from the sample. The null is 0. We divide that by the standard error, which is 0.22 divided by square root of 7, and we get 2.77. That's our test statistic. We compare that to our critical value. We can do this by using the student's t-curve or inverse t on a calculator. We're looking at 90% to the left. This is an alpha of 10%, and it's a right-tailed test. Our critical value is 1.44. Therefore, reject the null. We see that the test statistic lies in our critical region. Therefore, again, we reject the null. There is sufficient evidence to show that there is an increase in GPAs at the 10% significance level. So in other words, that the participation in learning communities does raise the GPA, and there's significant evidence to show that. So we've answered the question, but we're going to look at the p-value as well. I go ahead and draw my normal curve again, and if I were doing this on a calculator, This is simply a t-test because we're doing a t-test on the differences. So you could either plug in the statistics that we already found, that our null is there's no difference, our mean difference was 0.23, standard deviation of 0.22, and we want to look at our to see if there's an increase for the alternative, and we go ahead and we find that our p-value is 0.016, it's less than 10%, so we reject the null. The other way we could do it is we could put this as stats and list 3, and data and list 3, and we could do our test that way. So our p-value, because this is a one-tailed test, is just 1 times the area to the right of 2.77. On our calculator, another way we could do that is just type in TCDF, 2.77 and some large number because we're going infinitely to the right, and our degrees of freedom are 6, or 7 minus 1. That's 0.01, that's our p-value again. Therefore, we reject the null with a 0.016. That's definitely less than 10%. That's less than our less than our significance level, and therefore that's unusual at a 10% level. Reject the null, there is a difference. All right, I've entered in the data for the post in Staccato and the pre in Staccato. I'm going to go to statistics, hypothesis tests, matched pairs. My first sample is in post, my second sample is in pre. I'm going to use the significance level of 10%, and my alternative hypothesis is greater than. I click OK, and it gives me again my p-value of 0.0166. My test statistic is slightly different because I'm using data and not rounding.